Okay, so we will start this last session with Liang Ying Chih from JILA, and she will talk about reinforcement learning for designing matter wave interferometer. So please start.
Okay, hello. My name is Lillian. I'm from the University of Colorado, Boulder, and JILA. And today I'm going to talk about how we use reinforcement learning to design a matter wave interferometer. Since this audience comes from different backgrounds, I think it's helpful to mention that the field I work in is called quantum metrology or quantum sensing. In this field, people use quantum technologies to make measurements with the highest precision that no classical counterparts can achieve. One important tool in quantum metrology is the atom interferometer. And this is a technique that utilizes the wave-like properties of atoms to form interference patterns. It's commonly used to measure gravitational signals, and recently it's also been applied to measuring fundamental constants. The application that we're interested in is space navigation. And for this navigation, we need to design the atom interferometer so that it can measure acceleration and rotation with high precision. It's worth mentioning that even though my work is purely theoretical, the actual device is being built in our collaborator Dana Anderson's lab. And Penny Exeret, who's an aerospace expert, is helping us to make our device useful in space. And this wonderful collaboration is a part of the QSense grant awarded to CU Boulder. So let's start from the basics of interferometry. The most common type of interferometry is the so-called Mach-Zehnder Interferometry. In the optical version, there's typically a beam splitter that splits the light field into two paths. And then there are two mirrors that reflect these paths, and finally a recombiner. After the lights are recombined, we can look at the interference pattern and infer what the phase difference between the two paths is. In the matter wave interferometer, light field is replaced by matter waves. And in the most common Bragg diffraction interferometer, these optical components are replaced by laser pulses. So initially, the atoms are prepared in a certain momentum state. And after the first pulse hits, the matter waves is split into two paths. And the momentum difference between the two paths is 2h bar k. And then the second pulse reflects the paths, and the final pulse recombine the two paths. If this sequence is carried out in a gravitational field, then the two paths would accumulate different phases, and from the interference pattern, we can infer what gravity is. So our system is based on atoms trapped in an optical lattice. An optical lattice is a standing wave formed by two counterpropagating lasers. And by tuning the relative phase between the two lasers, phi of t, we can essentially shake this lattice. And this gives us control over the wave function of the atoms. The goal of this project is to design the shaking function so that our device can measure inertial signals such as one-dimensional acceleration with high precision. So we're going to use this, we're going to build a Mach-Zehnder interferometer in this shaken lattice. And to do so, we need to design the analogous optical components, the beam splitters, the mirror, and the recombiner. This entails carefully engineering phi of t so that the atoms in the lattice are split, reflected, and recombined. There are a few challenges in designing the components. One is that our system is highly multidimensional, meaning that it involves multiple momentum states. And all these momentum states can be coupled together by the lattice. And the coupling is very complex because of the time varying phase. Since this is not a two-level system, it's difficult to solve analytically. And I think it's safe to say that there's no intuitive way to design the shaking function for our purpose. So we think that reinforcement learning may be useful in this case because it's been applied to find near optimal strategies when it's impossible to do a brute force search. And it can also discover strategies that beat human intuition. So you've probably seen this from the previous lectures, but as a reminder, this is the general framework for reinforcement learning. It's basically a feedback loop between the agent and the environment. The agent evaluates the actions based on the current state and execute an action. Then the environment responds to this action and returns the next state and a reward that evaluates how good the state is. The goal of this learning framework is to find a strategy that maximizes the long-term rewards. So the first task that we apply reinforcement learning to is to design the beam splitter. Essentially, what we need to do is to transfer the initial ground state to a superposition of the left moving state and the right moving state. In practice, we transfer the ground state to the third excited block state. The block states are the eigenstates of this lattice. In this lattice system, momentum is discretized into integer multiples of 2h bar case. And this first wave function shown here is the ground state wave function. As you can see, most atoms, most of the population is in the zero momentum state. And the third excited block state, which is our target state, is a equal superposition of the +4 h bar k state and the -4 h bar k state. And we set this as our target state because it has a right moving component and the left moving component. And since this is an eigenstate of the system, it will be stationary during free propagation. Once we get the splitting protocol, the recombining process is basically the time reversed process. And the recombining protocol would transfer the third excited state back to the ground state. Now here is how we map our problem to the reinforcement learning framework. The agent that we use is a deep Q learning algorithm, which I will explain more later. The actions are chosen from a discrete set of phases, and during each step, the phase remains a constant. The environment is the quantum system evolving according to the Schrödinger equation. The state is defined as the populations in the momentum eigenstates. And this is a real observable in experiment. And to distinguish this state from the quantum state, I call it the observed state. We define the reward to be a function of the fidelity compared to the target state, which is the third excited block state. And the optimal policy represents a sequence of phases that results in the highest final fidelity. Here's more detail about the deep Q learning algorithm. We have a neural network that takes the state as input and output the Q values for each action. The training process is basically making this neural network learn the Q values so that it can represent the total discounted reward well. And because we want to maximize this total discounted reward, most of the time we choose an action that has the highest Q value. But because we also want to explore the state space as much as possible, for epsilon probability, we make a random choice for the action. Here are some results that we get from the deep Q learning algorithm. Up here is the splitting protocol, the phase as a function of time. As you can tell, the phase takes discrete values. And down here is the momentum distribution as a function of time. Initially, the state is prepared in the ground state. And after we apply the splitting protocol, it ends up in a superposition of the +4 and -4 state, as shown here. The second task is to design the mirror. And what this means is that we need to construct a unitary operator that maps any superposition of plus and -4 h bar k state to -4 and +4 h bar k states. The unitary operator follows the Hamiltonian evolution, and our mission is to design this phi of t so that U realizes the mapping that I just mentioned. This problem is fundamentally different from the previous one because we have a target operation problem instead of a target state problem. So similarly, we map our problem to the reinforcement learning framework. The action here is a discrete set of amplitudes for a sinusoidal shaking function. And each step is a half cycle of the sinusoidal oscillation. The observed state is the matrix elements that of the U unitary operator that we think are important. The reward is defined as a function of the channel fidelity. And this is a measure of how close U is to the desired operation, in this case, the reflection operation. The environment is the quantum system, and the optimal policy is a sequence of phase amplitudes that result in the highest final channel fidelity. So on the right is the result for the reflection protocol. Up here is the phase as a function of time. And as I mentioned, the amplitude is chosen every half cycle of this oscillating pattern. And to test the efficacy of this shaking function, we first prepare the state in the -4 h-bar state. And we can see that after applying this protocol, most of the population is transferred to the +4 h-bar state as expected from a mirror. After we get the individual components, we can combine them to build the entire interferometer. In this first region, we apply the beam splitting protocol. And in the second one, we set the lattice phase to 0, allowing the matter wave to propagate freely. As we can see, the matter wave is split into 2 paths in real space. And this is an evidence that our beam splitter works well. In the third region, we apply the reflection protocol. And as you can see, during free propagation, the matter waves are brought together again. And finally, we apply the recombining protocol. After this, we can look at the interference pattern to determine the acceleration. So this is what the interference pattern looks like. Each vertical slice is the probability distribution of momentum for a certain value of acceleration. Although this pattern looks complicated, what's important is that each vertical slice is unique, and it acts like a fingerprint, which allows us to estimate the acceleration from this complicated pattern using a Bayesian analysis method. So here is the Bayes theorem for just one measurement of the momentum. If we make multiple measurements, then we can calculate the probability distribution of the acceleration according to this formula. As an example, I pick an arbitrary acceleration and sample from the corresponding momentum distribution. As you can see, for the first few measurements, the acceleration, the probability density for acceleration is very flat. But as we draw more samples, the distribution becomes narrower. And at 100 measurements, we can see that the peak coincides with the true value that I picked. This means that our estimation is unbiased. And here is the standard deviation for acceleration as a function of number of measurements. For large number of measurements, the standard deviation scales as 1 over the square root of n, which is consistent with the standard quantum limit since we're using independent measurements. And in fact, n can be represented by the number of atoms in the lattice. So we don't need to actually make 10,000 measurements to get the precision as shown here. We use the Bragg interferometer as a baseline to benchmark our shaken lattice interferometer designed by reinforcement learning. And we found that using the same amount of time, the Bragg interferometer enclosed a smaller area in space. And because the sensitivity is proportional to the enclosed area, the shaken lattice interferometer is more sensitive than the Bragg interferometer. And this can also be seen from this plot of the standard deviation. So for this talk, I've told you how we design control protocols for a matter wave interferometer using reinforcement learning. And we do a Bayesian analysis to estimate the acceleration from the interference pattern of the interferometer. From our analysis, we found that the shaken lattice interferometer performs better than the conventional method. If you're interested in more detail, please take a look at our paper on arXiv. So in the future, we will use this design framework to implement this design framework in real experiments. And since our learning algorithm is model-free, we can simply replace the environment with real experimental apparatus. We want to use reinforcement learning to learn protocols that take advantage of atom-atom interactions. And also, since the Mach-Zehnder configuration might not be the optimal configuration for measuring acceleration, we also want to use reinforcement learning to learn configurations that give the optimal sensitivity. That's it for my talk. Thank you.
Thank you very much. Are there some questions?
Thank you for this great talk. I really enjoyed it. I just have like one experimental question just out of interest, because I have like no idea about this. Because you mentioned that you're like when you're doing this reflection, you're realizing this basically just by changing this wave of this laser, right? Is this like the same what you're doing when you're exciting the state like from the ground state to n equals 3 at the beginning in the beam splitter, or how are you realizing this experimentally?
So experimentally, the phase, so the experimentalist used an AOM to shift the frequency of the laser, and the frequency, the time integral of the frequency is the phase. And so by ramping the frequency, they can control the phase very precisely. So they can do like these discrete phase jump, and they can also do this kind of modulation.
Okay, cool. Thank you. Yeah, thanks.
Are there more questions? If not, let's thank Liang again, and we can pass to the next speaker.